Let's convert 69 to binary. How does a computer represent data? Well, a computer works with binary numbers to represent data, and often the CPU, the central processing unit within a computer, will read series of zeros and ones to do the instructions that a program or app that you wrote or other people wrote as instructions so that it can provide an output, usually on a monitor. So let's look at what a binary number system is, because a processor in a computer deals with zeros and ones. Binary number systems, is a base 2 system. There are two possible values in for a binary number digit, which is 0 and 1. If we examine the number 42,069, it's a number that is within the base 10 system, which is our normal human counting system, where each individual digits in a number will have a number from 0 to 9. So in this number here, we have a 5-digit base 10 number with us having 4, 2, 0, 6, and 9, and this ends up being 42,069. Okay. However, if we were to represent this number in a binary number system where we can only use zeros and ones, we get this long binary number: 10100, reading from left to right. So each digit in a binary number can only be 0 or 1. 0 means off and 1 means on. Okay. And that is how a CPU inside a computer will register this integer or positive natural number as a computer. It will have to read it like this as a binary number with a series of having off and on instructions. Okay, so let's talk about a bit. A bit is a binary digit. It's a single unit of data that a computer can understand, and a bit can be either or 0 or 1. And when you start to have series of these, you get to create larger data. So we create a byte, a smallest unit that is storable on a hard drive, and it contains 8-bit. So we can say that a byte can represent values from 0 to 255. For example, if I have 00101010, that is 42. Right? In binary, 001010 represents 42 as a decimal. And if I were to turn all the 8 bits on, we get 255, which is a calculation of 2 to the exponent of 8, which is the number of bits that we have, which is 8 bits, and we're going to subtract 1 because we started counting from 0. And if we were to talk about kilobyte, the term kilobyte means there are 1,000 bytes, and a gigabyte means there are 1 billion bytes. And that's how our unit of measurement goes when we talk about file sizes and app sizes and so forth. And when we're in a base 2 system, when we talk about binary numbers, we are talking about powers of 2. So if we were to represent the number 69 as a binary number, we get 1000101. With the leftmost, which is called the most significant binary digit or a bit, will be 2 to the exponent, the size of your binary number minus 1. In this case, we have 7 binary numbers, so we have 2 to the exponent 6. Okay. If that bit is turned on, we get to add that value to our total. If it's not turned on, if it's a 0, we don't need to add that value of the power into our total sum. In this situation here, we have this one, that one, and this very last one as the bits that are turned on. So we add the respective powers there. So 2 to the exponent 6 is turned on, 2 to the exponent 2 is turned on, and 2 to the exponent 0 is turned on. The rightmost bit should always represent the 2 to the exponent 0 power. So that gives us 64 plus 4, that gives us 68. And if we were to add 1, that gives us a decimal value of 69. And that's how we can have binary numbers representing numbers that we are comfortable with in a base 10 system. So let's talk about positive integers. Positive numbers can be directly translated into a binary number, and often for this scenario, we're going to work with 8-bit systems, as in we're going to look at, well, what values can a single byte represent? Okay. So to convert a positive integer to binary, we're going to do the following algorithm instruction. We're going to constantly divide the number by 2 and track its quotient and the remainder. Once the quotient, the Result of our division is 0. We stop the division of 2. And the remainders that we have tracked, if we go in reverse order, bottom to top, we can lay them out left to right, and that will generate the binary number of our interest. So if I were to divide 69 by 2, it's not a perfect division, so we get 34 and a remainder of 1. Then we take that 34, we divide by 2 again, because that division by 2 did not result in us getting a 0. We're going to do 34 divided by 2 gives us 17, remainder 0. 17 divided by 2 is 8, but not a perfect division, so we get a remainder of 1. Then we go 8 divided by 2, which is 4, remainder 0. 4 divided by 2 is 2, remainder 0. And 2 divided by 2 is 1, remainder 0. And then we do 1 divided by 2, which is impossible, so we get 0 and a remainder of 1. Okay, so we have reached 0. We can stop dividing. Now I analyze a remainder. The very last remainder you have generated will be the most significant binary digit you created, which will be the leftmost value of your binary number. So we go 1, then 0, 0, 0, and then we have the 101 to end it off, and that is 69 as a binary number. Right now, there are 7 bits, so it is often, if you are left at 7 bits and you are working in an 8-bit system, we'll just add a 0 at the front so that we get 0, 1, 0, 0, 0, 1, 0, 1 as a 6 to represent 69 in this type of scenario. Okay. So let's talk about Java. In Java, we were restricted with integers having a storage size of 4 bytes. So what does that mean? What values of integers can I represent with 4 bytes? Well, 4 bytes means for each byte there are 8 bits. So if we do 4 times 8, there are 32 bits of information that we can generate with 4 bytes. Okay. Now, when we work with integers, most often the leading bit in that number of bits that you have, right? The maximum number of bits that you have in this scenario, which is 32. The leading bit will always lead us off with either being 0 and 1, telling us 0 for positive, 1 for negative. It is because when we're dealing with a negative number, the very first binary digit being turned on is used and denoted to be letting us know it is going to be a negative value. So with this being 0 and everything else being turned to 1, we get to generate the largest possible positive integer value that we can create within Java as a variable for an integer variable, which ends up becoming 2,147,483,647. On the other hand, if we were to just have the very leading digit turned on and everything else turned off, we get to generate the smallest negative number that we can generate, which is negative 2,147,483,648. So that is the lower bounds of our integers that we could create in Java, and the upper bound was this number. Okay, that is because the very first binary digit tells us if it's 0, we're going to be dealing with a positive number, and if it's 1, it's going to be a negative number. In our next video, we're going to learn how to convert negative integers into binary number as well, so stay tuned for that. Now, numbers are fun, but we often utilize text in computer science as well, so we're going to talk about ASCII tables that helps us represent characters and strings. If you see this message above, that is a binary number message where it has been encoded to say hello with an exclamation mark, because these individual characters and symbol, they have a binary number attached to them. And depending on what type of encoding system you use, they may have different binary numbers, but right now we have H set to 01001000, and we're going to learn where that comes from. And that comes from the American Standard Code for Information Interchange, which stands for ASCII encoding. ASCII is an encoding table that maps a certain character, symbol, or digits to a binary number. And we use 1 full byte to represent different values in our ASCII table, but we can only generate 128 possible characters. It's because the convention was that when we use ASCII encoding, our leading bit was always going to be 0. Therefore, if this remains as 0, and if all our binary digits were turned on to 1, the maximum value we were able to create was 127. Therefore, in the ASCII table, we only have 127 values that we can represent by using binary numbers. So from 0 to 31, these were our control characters, which are special keys that often can be found around a typewriter. Then 32 and 126 were printable characters, such as the alphabetical characters from A to Z for both lower and uppercase, all the punctuation marks that we would use, and special symbols, and also the digits from 0 to 9 were all stored from binary numbers of 32 and 126. And the very final value that we can generate using the ASCII table, it was the delete character on a keyboard. So when we look at ASCII table from 32 to 63, so 00100000 represents the space key. So if we were to click the space bar on our keyboard, it would be registered to 00100000, and that's what the CPU would receive to register that you have pressed the key, the space key. Okay, so from 32 to 63, we get these types of value like space, exclamation mark, all the way to having all of our digits combined and some punctuation marks and so on. Okay. Next, from 64 to 127, we get an @ symbol, but more importantly, we get our alphabetical system, capital A to Z and lowercase a to Z, with some other punctuation and special symbols that is important to the English language. So this raises an interesting behavior when we're programming, because since 65 is encoded to be A, it is considered to be less than a lowercase a. On uppercase A, when we use them in a comparison or logical comparison of is something greater than something, we can say that 65A is actually technically less than lowercase a, because the encoding of capital A is 65 and the encoding of lowercase a is 97. Therefore, ultimately, lowercase a is greater than capital A. If we can represent numbers and text through the use of binary numbers, we can also represent colors and pixels. A pixel is a single dot of an image, and an image is composed of many, many different dots. For example, if you had an image that was 1920 by 1080 pixel, that means there are 1920 times 1080 amounts of pixels to generate that image. Well, a single pixel requires 24 bits of information to generate that color at that single dot of pixel. And we reserve 8 bits per color of red, green, and blue. Okay. This 8-bit allows us to have a value of 0 to 255, which represents the intensity, how intensely those respective colors of red, green, and blue are turned on. Sometimes we use also a 32-bit color system as well, whereas the final 8 bits will tell us how transparent that pixel is. So to see some example, if I want to generate the most maximum red values possible, I would turn the R 8-bit to 255, turn green and blue off so we get a full red, and so on. Green will be just the green being extremely maximum intensity to 255 and having red and blue turned off. If all red, green, and blue are turned on to their maximum values of 255, we get white. If all of red, green, and blue are turned off, we get black. And once we start mixing these values together, we get to create more diverse system of colors. If we're talking about resolutions and pixels required, a 1080p resolution, let's say we were watching a video that is in 1080p, that means a single frame in that video requires 1920 by 1080 pixels, which is 2,073,600 pixels just to create that one frame in that video, and that frame will require 24 bits of information. Whereas if we were watching a 4K video, each frame in that 4K video requires 3840 times 2160 amounts of pixel, which is 8,294,400 pixels. And each of those pixels will require 24 bits of information as well. So as you can see, just by going from 1080p to 4K resolution, the number of bits that needs to be either calculated by the CPU, or since we're dealing with images, the GPU has to process becomes extremely large. Because binary numbers, once you start to get long numbers, it's really hard to represent. We also have a hexadecimal system as well. Base 2 is binary. Base 10 is normal convention, where we as humans count from 0 to 9 every day. And hexadecimal is a base 16 system, so it uses the powers of 16 to generate different numbers that we may see in base 10. I want you to examine 314. It is the sum of 310 and 4. There are 3 digits, and at each digit location, we can have the numbers from 0 to 9 because it's following a base 10 system. 314 can also be represented as 3 times 10 to the exponent 2, 1 times 10 to the exponent 1, plus 4 times 10 to the exponent 0 to create 314. And that is the legitimate way how a base 10 system would calculate numbers that we were interested in. And similar to the binary system, the rightmost digit represents the number 10 to the exponent 0 we have, and the exponent will increase as we add more digits to it. And along that note, let's try to represent 314 as a hexadecimal. The characters represent these respective numbers. In hexadecimal, there are 16 possible values. We go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we go then A, B, C, D, E, F, where A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. The problem with these numbers is that they require 2 digits to represent those numbers. Instead of using up 2 digits to represent such numbers, we've reserved and added new characters to the system so that A would mean 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Therefore, a single hexadecimal digit represents the number from 0 to 15, F being 15. If we were to combine 2 hexadecimal digits, we get to represent numbers from 0 to 255. And if we add another hexadecimal digit, our upper bound increases dramatically, where we can represent numbers from 0 to 4095, which is far superior than base 10 system being only able to do from 0 to 999. And if we wanted 314 as a hexadecimal, we get the value as 13A. And let's see where that came from. Just like how we would convert positive integers to binary numbers, if I want to convert a base 10 number into hexadecimal, we repeatedly divide by 16 this time and then track the remainder, and then we follow it up backwards. If I were to divide 314 by 16, I get 19 with the remainder of 10. 10 is not hexadecimal, but we can represent that as A. 19 divided by 16 gives us 1, remainder 3. 3 is just 3 in hexadecimal. And 1 divided by 16 gives us 0 with the remainder of 1, where 1 is still 1 in hexadecimal. Therefore, we have 13A as hexadecimal for 314. So if we were to calculate and make sure we have done this correctly, we're saying we have 1 of 16 to the exponent 2, 3 of 16 to the exponent 1, and we have a many 16 to the exponent 0, which is a multiplication of 10. And we add up all those numbers, 256 plus 48 plus 10, we get 314. Therefore, hexadecimals, these are the digits that we can create. We have 16 possible options, and so on. And why is this useful? This is useful for colors, because if we had to represent 255 and 255 and 255, we would need 24 bits, a 24-bit long binary number to represent it. However, since every 2 hexadecimal values can represent the numbers from 0 and 25, we just need 6 digits or characters from the hexadecimal set to represent colors. And you will see often graphic designers or web designers having certain special colors memorized as hexadecimals. To just quickly end off this video, there is a prefix to denote that we have such numbers or number systems being in place in a programming language setting. So if there's no prefix, it is kind of assumed that you're working with a base 10. But if there's a 0b as a prefix after a series of zeros and one, before a series of zeros and ones, the computer will recognize that you are dealing with binary numbers. If there's a 0x as a prefix, then the rest of the characters afterwards, or numbers or digits, will be considered to be in a base 16 system. So that is it. This is how at a very basic level, a computer can represent data and how we can encode binary numbers to different systems and to show different things like text and color. And this is how a computer works with binary numbers. And as always, thank you for watching and stay classy.